Hey everybody, so this is the first of the online lectures for Math 470 Modern Algebra 2 at CNU in the spring of 2020. We've had to move online due to the COVID-19 pandemic, and well, we're just going to see how this goes. Couple of things up front. Format of the material presented here is going to be a little different from class as necessitated by the online nature. My suggestion would be that you print the slides for each lecture from Scholar, make notes on them as I go through the screencast, record any questions that you have along the way, and then when it's officially class time, use the Google Hangout that I have set up for this class to ask specific questions about lecture material, and we can also talk about homeworks during office hours and other things, but I want to try and reserve the specific class time for lecture questions. I apologize also for the rough delivery on these things. Due to the time constraints, I am doing little to no editing on these videos, and I'm prioritizing content versus delivery. Hopefully, as things smooth out and I know the online transition is going well, I will have more polished scripts and there will be less mistakes in what I say as I try to remember exactly what I was thinking when I typed up the slides. I'm also going to try and subdivide the videos or try to subdivide the lectures into smaller videos. So there might be 2 or 3 videos per what would be a classic lecture. I just sort of feel that if it's subdivided into smaller units, it'll be easier to follow and easier to parse what's going on. I'm going to try to roughly keep it so that there's one major topic per video. That topic may be a main theorem with some applications, or it may be sort of more general problems, but basically keep it geared around one result. Okay, so we're going to be starting with what I've called part 2 of field extensions. Part 1 we've already done in class. I just didn't call it part 1 because I didn't realize we'd be doing it in this fashion. Okay, so we are trying to determine the structure of a field extension where we take a base field F and we adjoin an element to it alpha. Alpha falls into one of 2 general categories. One is transcendental and the other is algebraic. We've taken care of the transcendental case. If alpha is transcendental over F, so it doesn't satisfy a polynomial relation, then every one of these expressions are completely distinct from each other. None of them are 0. And essentially, a transcendental element behaves exactly the same algebraically as an indeterminate. So when I take this, I get a nice closed ring. It'll be an integral domain, and it's isomorphic to the polynomial ring. But since it is an integral domain, it has a field of fractions, and so F adjoined alpha, the smallest field containing both F and alpha, is that field of fractions. This is the so-called the field of rational functions. All right, well, that begs the question, what about when alpha is algebraic? Well, that's what this video is for. All right. Now, we've established a few general facts that we're going to need. Apparently one very general fact and one more specific one. The very general fact that we need is that whenever you have 2 fields, one contained in the other, the larger field is a vector space over the smaller field. All right. This dimension is sometimes called the index and it is written in this form. This can be infinite. For example, if E was the transcendental extension by some transcendental alpha, that would definitely be an infinite dimensional extension. But for us, most of the time, this dimension will be finite. So everything that you know about finite dimensional vector spaces will apply here. The other thing that, we have learned about is that when we have an algebraic polynomial, what really makes it algebraic is it satisfies a polynomial relationship and I get 0. All right. The polynomial of minimal degree that satisfies this is called the minimal polynomial. We require that it be monic. In particular, that makes it unique. The minimal degree requires it to be irreducible. Okay, so last class, before we were so rudely interrupted, we had established the following. So if I take an algebraic element, alpha over f, and I have its minimal polynomial, if I look at a set of powers of alpha, if I start with 1, which is alpha to the 0, up through alpha to the n minus 1, so 1 less than the degree of the minimal polynomial, I get a linearly independent set. All right. On the other hand, if I take 1 more power, I get a linearly dependent set. All right. This is key in what we do, because what we're going to do is we're going to take that linearly independent set and we're going to take its span. So we're going to take all possible linear combinations of 1 alpha, alpha squared up through alpha to the n minus 1 using coefficients from f. When we do this, this is going to actually be a field, and this is dependent upon alpha being algebraic, as we will see. But once we show that it's a field, we're going to show that this is indeed f adjoined alpha, i.e. the smallest field that contains both f and alpha. Okay, so recall again the span, as I just said. This is all linear combinations, and again, my coefficients are coming from f. All right, so before we get into the proof, let's go over what exactly we're going to need to demonstrate. Now, we need to show that it's closed under addition. That's gonna be simple. All right, closure under multiplication is going to take a little bit of work. What it's going to hinge upon is that I am taking powers of alpha up through the n minus first, and when I multiply 2 of those powers, it's very easy that I could get something of power n or higher. I'm going to need to show that I can rewrite something of degree higher than n as something as a combination of those lower than n minus 1. All right, that will get me the closure. I need to show that this is going to form a ring. That's going to follow very quickly from the work that we do for addition and multiplication. The trick is going to be the field. All right, we need to show that every element in there is invertible. All right, so we're going to be taking sums of powers of this algebraic element, and we have to show that this sum is somehow going to be invertible. If you think about that, that's a little tricky. Showing a sum is invertible under multiplication is much harder than showing, multiples of things are going to be invertible under multiplication. Okay, so let's start with closure under addition. All right, so the elements of K, they are linear combinations of the powers of alpha. So if I take 2 elements in there we go. Let's call them U and V. So one is some linear combination with coefficients Ci, the other one is coefficients Di. If I take their sum, well, then it's essentially a component-wise operation. So I'm adding the coefficients of each one, all right, for each power of alpha. Likewise for their difference. Why am I showing the difference? We're going to want that later when we're showing something as a subring. Okay, but every element in K is a linear combination of powers of alpha. We've shown that if U is a linear combination and V is a linear combination, then U plus V is also a linear combination. All right, that gives us that K is closed under addition. Now, closure under multiplication is going to require a little bit more work. All right, so the base claim that we need to establish is that if I take some power of alpha which is larger than n minus 1, it still belongs to K. This means I have to be able to write alpha to some power as a linear combination of 1 alpha, alpha squared up through alpha to the n minus 1. Okay, so I've said our base case is for all n greater than n minus 1. We could take our base case to be n minus 1. I don't. I want it to be taken as n. We're going to proceed with induction. The nth case is very simple. We use our minimum polynomial. So we know that for our minimum polynomial, and there is a typo, that should not be subscript, that should be a superscript. And I'm sorry I missed that, but it'll get fixed on the next line. Okay, so I know if I take the sum from 0 to n, alpha I, a sub I, alpha to the I get 0. The minimal polynomial is monic, so I can split off the alpha n, push all the other terms to the other side, and that does it. In equation 4, we see that we have alpha to the n expressed as a linear combination of the powers of alpha ranging from 0 to n minus 1 simply by breaking up the minimum polynomial. Okay, so now we'll state our induction hypothesis. I'm going to assume that alpha to the n belongs to k, which again is the span of powers of alpha, and once again, there's another typo. Okay, so by assumption, I can write alpha to the n as a linear combination of the alpha powers from 0 to n minus 1. All right, so I'm going to take that equation, and I need to know about alpha to the n plus 1. I will simply multiply both sides by alpha. All right, well, when I do that, on the left-hand side, I get alpha to the n plus 1. On the right-hand side, I increase every power of alpha. So the powers of alpha now run from 1 to n. Okay, so I'm going to split off those that are between 1 and n minus 1. All right, so I is going from 0 to n minus 2, so I plus 1 is going from 1 to n minus 1. And then I'll pull off the term alpha to the n. Okay, so that gets me this. This is just the whole thing recopied again. All right, I'm going to re-index it just for hopefully clarity. I'll take j to be I plus 1. I will make a new coefficient, d sub j, which will be c sub I plus 1. And then this last one I'm just going to simply call d. Okay, when I do that, I now have this written as powers from 1 to n minus 1. So this part here belongs to k because it's a linear combination of powers of alpha between 1 and n minus 1. I could go down to 0, but I don't have to. And then I'm left with this term here, which technically isn't a power between 0 and n minus 1. But our base case took care of that for us. We know how to write alpha to the n in terms of the lower powers of alpha. All right, I'm just using that minimal polynomial relationship. So I can plug that in to equation 9. All right, well, this is combinations of the powers between 0 and n minus 1. This is combinations between 0 and n minus 1. Closure under addition, that belongs to k. So equation 11 gives us that any power of alpha by induction belongs to k. All right, well, now that we know that any positive power of alpha belongs to k, we can prove closure pretty quickly. If I take two elements of k, so two linear combinations of powers of alpha, I multiply them together. Again, I get some large convoluted sum of powers of alpha, which may go well above n minus 1. But I know that anything above n minus 1 is also in k, so I am adding elements of k to elements of k, and it's closed under addition, so everything sums of powers of alpha. All powers of alpha belong to k, their sum belongs to k, and the whole thing is closed under multiplication. All right, so that takes care of the two closure parts. Now we want to show that it's actually going to form a ring. All right, well, by assumption, F was a subfield of E and alpha is an element of E. So all powers of alpha and all multiples of alpha by elements of F all belong to E. So in particular, K, whatever it is a subset of E. For me to show that K is indeed a subring, to show that it is a ring, all I therefore need to do is show that it is a subring of E to make certain that I have distributivity, etc. All right, but we've essentially done that. 0 is in there because I can just take 0 times every power of alpha, add those together, that gets me 0. We showed that it was closed under subtraction. We've shown that it's closed under multiplication. Hence, we are going to get a ring. Now, the important part, though, isn't so much that it's a ring. I mean, distributivity, etc., were going to be inherited from E. That wasn't the big deal. It's the fact that it's a subring of a field. All right, now, subrings of fields are not always fields, but they are always integral domains. Okay, so whatever this K thing is, I've got cancellation laws. I don't have to worry about zero divisors or anything like that. That's going to be critical in the next step, which is really where all the work comes in. We need to show that there are inverses. Okay, that's what makes a field special. Every element is invertible. Now, the way to do this is to use linear algebra. There is not a formulaic way to show that some linear combination of the powers of alpha has an inverse. We can't come up with a sort of algorithm for determining these inverses. We're going to use the fact that we have a finite dimensional vector space. And I stress it's very important that it's finite dimensional. This will not work in the infinite. All right. So we take these powers 0th power through the n minus first power. So n powers. This is an n-dimensional extension. All right. These are linearly independent, so they are necessarily a basis. The important thing to remember is that if I take any collection of vectors which is larger than the dimension of the vector space, that set of vectors is automatically linearly dependent. All right, now the way to use that. So we're going to start with an element U and K, and we're going to assume it is non-zero. I'm going to take a bunch of powers. In particular, I'm going to take n plus 1 powers. All right. Because I've taken more than I have in the dimension, they're linearly dependent. Because of that, I can find a linear combination of them, which gives me 0, but the C sub i's are non-trivial. There's at least one term in there that has to be non-zero at least. There could be more. There almost certainly is. Okay? But if I do that, since I know that at least one of them is non-zero, I'm going to choose the minimal index where C sub m is not 0. So everything before then is 0. Everything after, I don't know, but I know that C sub m itself is not 0. So if there were 0 terms in the front, I'm just going to truncate them off. All right, so they're pulled out. I just ignore them. The advantage here, every term in this sum has at least a u to the m power. So I can factor that out, which I do. All right, so when I do that, I have 0 on the left-hand side. I have u to the m times this sum. Now, it's important to note the first term in this sum, so when I is equal to m, I have u to the 0. I have c sub m u to the 0. So I have a constant term on the right-hand side in this sum. I have this times u to the m is 0. And as I mentioned, we're in a domain. So I can cancel. U was non-zero, hence all powers of u are non-zero. So that means the sum has to be 0. All right. So now I've got the sum equaling 0. That's going to be useful, as we will see, because I know the first term in this is simply a constant. Okay. So I've just recopied the same statement. Now I am going to pull that constant term I talked about off. I'm going to pull it to the left-hand side and put everything else to the right-hand side. And again, there is a typo. There shouldn't be 2 c sub i's there. I will try to fix that for the online slides. Okay, so I just paused my recording and went and fixed that. So the slides you have on Scholar should be correct. All right, now, I know that c sub m is non-zero. That was my assumption. We did that from the non-trivial solution. So it has an inverse. So I'm going to multiply the whole thing through by negative c sub m inverse. On the left-hand side, I get 1. On the right-hand side, I get negative c sub 1 inverse. Ignore that c sub I times u to the I minus m. All right. But I minus m is running from m plus 1 to n plus 1. So every term on this side now has at least 1 power of m in it. So I can factor that out. When I do that, I have 1 is equal to u times this whole thing on the right-hand side of equation 21. But that's exactly what I needed. In order to show that u had an inverse, I needed to be able to show that I could take u and multiply it by something and get 1. Well, I've taken u, I've multiplied it by this, and I've gotten 1. So that means this beast is indeed the inverse. Okay. Well, that pretty much does it for us. We know that k, this span of 1 alpha up to alpha to the n minus 1, I know it's a field. Okay, so if I take any field L that contains f and it contains alpha, all right, well, L is closed, so it has to contain all powers of alpha. It has to contain all power multiples of alpha by elements of f. It has to contain all of their sums. So, in particular, all linear combinations of all powers of alpha must belong to L. In particular, this means that K has to be contained in L. That makes K the smallest field containing F and alpha. So when alpha is algebraic with some minimal polynomial, F adjoined alpha is the span of the powers 1 alpha up through alpha to the n minus 1, where the degree of the polynomial has degree n. All right, so this allows us to assign a degree to an algebraic element. From here on, when we're dealing with an algebraic element, if it's got a minimal polynomial of degree n, to sort of simplify matters, we'll simply say that alpha has degree n over f. So once we know that, once you encounter that it has degree n over f, that means you know 1 alpha up to 1 less power, alpha to the n minus 1, will form a basis of f adjoined alpha. Now, that gets us through the classification of extending a field F by either an algebraic element or by a transcendental element. But that's extending a field by one element. What if there are more? All right, turns out this is key to doing that, but there are other ways. There are more general extensions that we're going to have to look at. And we will pick up there in the next video.